In this video, we're going to start talking about how we can find the x-intercepts using square roots. And we have talked about different ways to find x-intercepts, and the goal really is the same for understanding x-intercepts. We always want to set the y-coordinate to be equal to 0 because the y value at x-intercept is always 0. So in order to do this, we're going to do the same here. When we want to find the x-intercepts, for example in part A, we just want to set f of x to be equal to 0 to start with and solve for x from here. And today we're going to focus on particularly the square root method in order to solve for x. And the square root method works really nicely when we have a perfect square expression in the equation already and one other constant by itself. So here, for example, we have x squared, which is a perfect square term, and we also have the other value being subtracted by 9. And when we have 9 being also a constant, that's easy to take the square root, and just one single term by itself, it becomes a lot easier to use this square root method. So in order to use the square root method, we want to get the perfect square by itself, and the constant should go on to the other side. And once we want to do this, we can add 9 on both sides, and that gives us 9 equal to x squared. And this is the step we need to take in order to use the square root method. And you can see in these examples, no matter what we start with, our end goal is to always have a perfect square equal to some constant number. And that's the only format the square root is going to work out nicely. Now if we want to find x, we can go ahead and take the square root on both sides. And when I take the square root of x squared, remember when we have a square root, it could really be two different values. It could be both positive or negative. So we want to use this to indicate that we are expecting two different answers that would both work. And in this particular case, we can see the square root of 9 can be positive 3 or negative 3. So we would say the answer in the end is plus or minus 3 is equal to x. And we use this notation for plus minus square root of a constant to indicate that we want to make sure we get both square root answers. And that's how we guarantee we will get two different values when we're working with this quadratic function. Now that we have the x value, we can say the x-intercepts in this case are 3, 0 and negative 3, 0. So these are the x-intercepts. And if this works out and makes sense to you, we can move on to something like in part B. And in part B, again, we have a perfect square subtracted by a constant. There are only two parts in this entire expression for the function, and that's where we know square root will work out nicely. So to find the x-intercept, again, I'm going to set the function value equal to 0. That's equal to 4x squared minus 25. Once we have this form, we want to get the perfect square by itself and the constant by itself as well. So if we want to get the constant by itself, we can add 25 on both sides, and we get 25 is equal to 4x squared. And from here we have a nice case that 4x squared completely is a perfect square, so you have some flexibility over here as to what you want to do next. So one option, if you recognize 4x squared is equal to a perfect square, is you can rewrite 4x squared as 2x completely squared. Because whatever we have on one side, we need it to be a perfect square. We don't want to deal with any messy numbers or things like that. That's kind of the idea. And in this case, it works out nicely that 4 is also a perfect square number. So once we have this form, what we can do is again take the square root on both sides, and we would get plus or minus square root values as a result. So square root of 25, if we take both positive and negative value, we will have plus or minus 5, and that's equal to 2x, because the square root and square cancel each other out. And now we're not quite done yet because we have 2x equals some number. So in order to get rid of that, we want to isolate x. So we can go ahead and divide 2 on both sides, and therefore x is equal to plus or minus 5 over 2. And then we can report the x-intercept in conclusion is 5 over 2, 0, and negative 5 over 2, 0 in this case. And we say that we have a little bit more flexibility in terms of what we can do here by taking the square root directly of 4x squared right away. And in reality, it might not always work that the coefficient always ends up being a perfect square like 4 as well. So this leads us to something that you might see in part C. And in part C, again, we start with some quadratic term and plus a constant term over here. Now if we want to find the x-intercepts, we can still use a square root method because we really only have 2 parts in this expression, the perfect square part and the constant part. But if you look at it, when we set h of x to be equal to 0, that gives us negative 3x squared plus 7 is equal to 0. And to isolate the variable part and the constant part here, I'm going to add 3x squared on both sides, just so I can avoid working with negative terms on both sides. So if I add 3x squared on both sides, I will get 3x squared equals 7. So you can see this step is pretty similar to what we saw in the second step in part B. And when that happens, in part B, I said 4 is a perfect square number, so we had a bit more flexibility to just directly take the square root on both sides. But here, that's not quite the case for 3. So one thing we could do in order to make the left side a perfect square, or the variable side actually a perfect square, is we can go ahead and divide away the 3 on both sides over here. And as we divide away 3, we get on the left side x squared, which is a perfect square term. And on the right hand side, we have 7 over 3. And you might think it's not a perfect square number, but that's okay. It's easier to have all the numbers together, all the constant parts together, when you don't have a perfect square. So in this case, when we take the square root, we are going to take the square root on both sides. Again, on the constant side, we want to indicate we want to take both positive and negative values. So as a result, we're going to get x is equal to plus or minus square root of 7/3. And this is a valid method to use. Even though our number doesn't come out nicely to be an integer anymore, this still indicates what our answer will be for the x-coordinate. But we want to do a little bit further in order to rationalize the denominator. And to rationalize the denominator, we want to go ahead and work with this radical expression a little bit. So we're really saying x is equal to plus or minus square root of 7 over square root of 3. To rationalize it, we're just going to multiply the square root of 3 on both sides, so we can get rid of the square root on the denominator. And once we do so, we're going to get on top, we have square root of 7 times square root of 3, which is square root of 21. And on the bottom, square root of 3 times square root of 3 should give you 3. And the end goal is that you shouldn't have any square root in the denominator. Therefore, our x-intercepts are root 21 over 3 comma 0 and negative root 21 over 3 comma 0. So you can see if we compare our solutions for parts B and C, their formats are very similar, where we have a leading coefficient that's not equal to 1, and we see there are really 2 ways we can deal with this case. When we have a perfect square, we could just treat them all together and take the square root, but you can also just universally divide away whatever the leading coefficient is whenever it's not equal to 1. And when that's the case, we just would have x equal to some value right away, instead of getting a result of 2x equals something, then simplify from there. So these are the 2 examples when the leading coefficients are not equal to 1. Now that we know how to work with the case where we have x squared in the expression a constant, we might have some other cases like we see in part D and on. So in part D, we have a perfect square expression subtracted by a constant, and this still fits our format that we're looking for in order to use a square root property. And to do so, we start off exactly the same way as before and say 0 is equal to x minus 5 squared minus 16. And then we isolate the constant away from the perfect square part. And when we're isolating the constant, we would add 16 on both sides to have 16 equals x minus 5 squared. And this again becomes this scenario when we have a more complex expression being squared, we can just directly take the square root on both sides. Just like in part B, we could take the square root of 4x squared completely, we can take the square root directly in this case. So if I take the square root on one side, I gotta take the square root on the other side and indicate I want both positive and negative answers. So I have plus or minus 4 is equal to x minus 5, because square root and square again cancel each other out. Now if we have this result, this tells me x minus 5 can be two different values. So in order to solve it, I'm really solving two different equations. And this is where you want to be careful since we're solving two different equations. Write it out instead of just trying to add 5 directly to this lumped together positive and negative 4. So we really have 4 is equal to x minus 5, or negative 4 is equal to x minus 5. So we can fully simplify the answer. Now if we want to solve for x, we can add 5 on both sides and get 9 equals x, or 1 equals x over here. So we can say our x-intercepts are going to be 9, 0, and 1, 0. These are the answers. And when we have a linear equation equal to positive or negative value, make sure you write it out to solve two separate equations, like we did in part D. And looking at the expression in part E, I hope you recognize that now we're combining this idea that sometimes our leading coefficient is not equal to 1, sometimes we have a perfect square expression that's not just x. So using all the knowledge we have from the previous parts, we're going to look at part E. Again, to start, I'm going to go ahead and say 0 is equal to the right-hand side. And then we want to isolate the constant by itself. Again, I like to avoid working with negative expressions on both sides, so I'm going to add the 3 times x plus 2 squared entirely. And that term goes to the left side, and then we have this is all equal to 12. So once we have this form, we have again a leading coefficient 3, which is not a perfect square. So we're going to do something like we did in part C and divide away that leading coefficient. So we get that perfect square expression by itself. So I'm going to divide 3 on both sides, and that gives me x plus 2 squared is equal to 4. From there, we can do the same step as what we did in part D by taking the square root of both sides and indicate you want both positive and negative answers. So x plus 2 is equal to 2, or plus or minus 2 over here. And from here, you can write this out as two different equations. We get x plus 2 equals 2, or x plus 2 is equal to negative 2. Then if we want to solve for x, we can subtract 2 on both sides to get x equals 0, or here if we subtract 2 on both sides, we'll get x equals negative 4. Therefore, our x-intercepts are 0, 0, and negative 4, 0. So we're really combining our knowledge about different scenarios here. And lastly, looking at part F, I hope you recognize that we have a lot more non-perfect square values to work with, but it really follows the same strategy as what we talked about before. If we set things to be equal to 0 and isolate the constant we can add 8 on both sides. 8 is equal to 5 times x minus 2 squared. So this is really not too different from what we did in part E, where we have a leading coefficient that's not a perfect square. So let's go ahead and divide away the 5 on both sides. And that tells me 8 over 5 is equal to x minus 2 squared. And to find that, we're going to take the square root on both sides, make sure you have both positive and negative, and therefore we have plus or minus 8 over 5, square root of 8 over 5 is equal to x minus 2 over here. And once we have this form, we can again go ahead and simplify what square root of 8 over 5 is before we go further, just so we have a rationalized form already. And in this case, we can see this is plus or minus square root of 8 over square root of 5. And in order to rationalize it, we would have square root of 5 multiplied to each side, and that's equal to x minus 2. And we would get just 5 on the bottom, and on the top, in case you didn't recognize it, square root of 8 can really be written as 2 square root of 2, because square root of 8 is equal to square root of 4 times 2. Here I'm just looking for perfect square numbers. 4 is the largest factor that's a perfect square going into 8. So that's really equal to square root of 4 times square root of 2, or 2 root 2. So a quick recap on simplifying the radical expressions. And then we really have 2 root 2 times root 5 over here. That's equal to x minus 2. And then if we want to simplify the numerator a little bit, we would get plus or minus 2 root 10 all over 5. That's equal to x minus 2. Now lastly, to solve for x, we can go ahead and add 2 on both sides. So we get plus minus 2 root 10 over 5 plus 2 is equal to x. If you want, you could combine the two values into one single rational expression, but this is somewhat optional over here. And if we want to list the final answer, we can say the x-intercept is going to be 2 root 10 over 5 plus 2, comma 0, and 2 root 10 over 5, negative 2 root 10 over 5 plus 2, comma 0 over here. And that's how we can find the answers to this type of problems over here.